networking, great food. I have the honor to announce the next blog, and we're starting with Corinna Weber from Snap. So it's a startup, and what's the startup doing is exactly what Corinna's going to talk about. What's the power of BCI, so brain-computer interfaces, in virtual reality? I'm super exciting, and the stage is yours.
Laura? Hallo? Soll ich jetzt das nehmen? Ja, hallo zusammen. Vielen Dank, Laura, für die Einführung und auch vielen Dank an Christian und Art für dieses Event. Sorry, in English, right? Okay, so thank you so much, Laura, and thank you, Christian and Art, for having this great event, and also for the speakers before, which were really, really impressive, the talks, and I learned a lot about VR. I think VR is a very, very still a blue ocean where there are so many possibilities, and it's so much fun to think about what the future will also hold for us. So I'm going to talk about brain-computer interfaces. I think the talk after me is also about a little bit about this topic. So I hope we don't collide too much, but also brain-computer interfaces for me a blue ocean where there's a lot of stuff to do. Beyond keys, it's the things I will talk about today is about active controlling with our thoughts and what we do at the company Snap. So I'm not from a university, I'm from the company Snap. And my background is electrical engineer. So yeah, so far so good. Okay, so let's start with non-invasive EEG, because that's what I'm going to talk about. There are many different types nowadays for BCI communication, which means that when we are thinking, we somehow interact with the technology. And this is Hans Berger, probably known from everybody sitting here. If not, I will repeat it a little bit. He invented, or he found, that the brain is having oscillations, 1924. And his first measurements, eventually, which worked, looked a little bit like that. And due to this experiments and his work, EEG became one of the most popular diagnostic methods for several disorders. For example, epilepsy, attention deficit disorders, hyperactivity disorders, concentration problems, a little bit Parkinson, multiple sclerosis, sleeping problems, and very other mental disorders. So what happens when you go to a clinic nowadays? In the neurology department, you probably will get an EEG because it's cheap, it's easy. If you look behind it, how an EEG looks, it's like that. So you have several electrodes on the head, and they measure the potential between the electrodes or from each electrode. And in the upper image, you see from a healthy person an EEG, and in the lower level, you see it from an unhealthy person. But I guess probably you don't see anything, because it's really, really difficult to see something from an EEG. And doctors who work with EEGs have to work for several years to get something good out. And it's still a topic where it's very hard to learn reading good EEGs, because it gets a lot of artifacts which overlap on top, because the brain signal has to go through the scalp and through the skin and hair, and it catches up a lot of inferences, so it's not very nice to read. Here you see the electrode position from a normal 2030 system in a hospital. And as you can see, the electrodes are verteilt, distributed over the head. Okay, so far for non-invasive EEGs. And what they figured out back then, because they figured out some points which were very interesting, is that you can divide the oscillation of the brain into different frequency bands. And these frequency bands give you some information about the different states of your mental conditions. So, for example, in the delta band, I'm sorry, it's going through here. You are very calm. Probably you are sleeping in a deep sleep. You're not focused. In the theta band, you are deeply relaxed. And for example, when you do meditation, you are in this frequency band. And so you can somehow divide these bands and bring them to your mental conditions. That's what they got so far. So this is twisted. Okay, so the higher the frequency, the more active you are from your mental condition and from other points of view. So they did know that these mental states were somehow connected to these frequency bands, and they could measure the frequency band by doing a short, fast Fourier transformation or some wavelet transformation. So that somehow got the frequency bands out. But what also is important to know is that we don't only have the frequency distribution, but we also have a spatial distribution due to the different regions of our of our brain. So we have different lobes which are mainly responsible for some actions in our brain. And this is also a very important point for active brain-computer interfaces. And as you probably all know, there's this homunculus. I don't know if I pronounce it correctly. In Germany, we call him homunculus. And you have, for example, here you see different regions, and these different regions are connected to, for example, activities of different movements or different body parts. As you see, we have here in this part the hand, which is very, very big in comparison to the feet, which is like in the middle, in between. And so we have two things. We have the frequency and the spatial distribution, which gives us information about what the human is doing. So by knowing that, we see how we get the information out. What we do is we do an EEG acquisition. And yes, we still do it old school. We still do it with gel electrodes because this still gives us the best signal. There are already some dry electrode systems out, but we don't like to work with them so much because the signal is not as good as with the gel electrodes. But I said in the beginning, we are a company, so we have to think of usability. This, of course, will never be the way to go. So the way to go will be dry electrodes. But to get the whole software pipeline behind it right and the whole machine learning pipeline right, we work with better signals. Okay, so we can either work with a few electrodes or with many electrodes. And again, the signal is better with many electrodes, but here we have our border. So as a company, we try to work with as few electrodes as possible in order eventually to bring it into a working system. So what we do is we do the data acquisition. We measure on the scalp the voltage of the head, and we get something out like this. And when we measure it, we don't measure it just for a certain period of time, because then we cannot know what in the brain is really happening. So we somehow have to synchronize it or label it with some experimental setup in order to know this EEG part was measured while, I don't know, a certain scenario was running on screen, a certain scenario on the VR, or the human was doing something. So we somehow synchronized our experiments, and then we do some EEG signal pre-processing, which has to be done because the signal is very, very noisy. As you can see, for example, here you have a very, very noisy signal in comparison, which probably is, they're called artifacts, and they are mostly done by body movements, muscle movements, eye blinking, in the way, the direction you look, or speaking, or some outer artifacts which overlap over the signal. So we somehow make the signal clean, and then we do a signal extraction, and we use either some components analysis, we do some machine learning parts to do that. Here, for example, you can see a spectrogram of the EEG signal I'm not sure if it's single or if it's multiple, but eventually you could see something in the measurements. And this is how you knew, for example, yeah, we have a desynchronization in this part. So it gives us some kind of hint that we can get something out of the brain signals. But since 4 years, we are also working a lot with neural networks in order to get out these signals more easily, because, yeah, AI also helps us here in this part. So what we do then is we somehow train networks in order to get out the classification and to see what the person was thinking. But there is no standardized procedure how to do that, because there are different, we call them I call them BCI paradigms, which can be tried to be detected. And somehow, right now, each of them uses different kind of algorithms behind it to identify them. Okay, so now I explained to you how we measure and how we get the brain signal out of the head into the computer. And now we need to think of what can we use in order to control, for example, a computer game. Because it is, even if the fantasy is probably pretty clear, everybody knows how they would interact. To bring it into a technical system is not as easy. So the company Snap comes from the movement parts. That's why we were concentrating on the last 4 years on the movement and to detect the movement of the body in the brain signals or the motor imagery. So when you think of a movement, you have similar brain activities and you can also detect that. This would be a spontaneous mental control signal, because I move my hand and it's spontaneous. I decide when I move it and I could get it out. So it's pretty complicated and not so easy. In comparison, also we have the evoked potentials, where you can somehow, or you get somehow from your technical counterpartner, you get a signal and your brain somehow reacts. For example, you have a flashing light and you can see in the visual cortex the frequency, and you can get out the frequency and you use it in order to say the person focused on this frequency. You can also have the P300 paradigm, which is a very nice one when you have something in a certain rhythm flashing and then something randomly flashing, and you tell the user to concentrate on the random flashing object. You can also tell when he concentrated on that part. So that's also a nice paradigm, but it's not as we think of freely controlled BCI systems. Okay, so why is BCI so disruptive? In order to understand why so many people see a big future in BCI, we have to think, okay, what can we disrupt with that? Because it's all about disruption. You want to corner the market there. So traditional input devices, that is probably what most people think of when they build BCI systems. We want to get this laser pointer away, right? I mean, it's a little bit also like the eye tracking talk before. It's when I want to, when I look at this upper button here, I don't want to use my hand and use the controller. I want the system on my head to detect it and to point it to you guys that I'm now looking at this one. So also the gesture control, which is probably not there yet, but soon hopefully will be more. I mean, it's already there, but we are not using it so much. I think in some cars they're using it already, the gesture control, or in the VR already also. But here also we try to, we think that BCI can cover a lot of that. Voice control, which is a very, very important part. It's we call it silent speech, so that you think of the commands and you think of sentences and you think of emails which you want to write, and the system detects it and writes it down. And of course, virtual reality, that's why you guys are all here. It's probably also for us the most important partner, because as I said before, the EEG data needs to be synchronized, measured to a certain surrounding. So if I would measure right now here my brain signals, and I don't have any other sensory input, we wouldn't know what to do with the brain signals. But if I do it in a defined VR scenario, it gets way nicer because I can see, I don't know, the car is approaching me, and I label it by that. And I can, I don't know, make the mood by color changing, and I label the brain data by that. And then I can train and classify, and so on and so on. So we really like virtual reality. But also other parts, which I don't go too much into it, are very important. Oh, I also don't have a time, so somebody here needs to tell me when I'm when I'm done. Which is very important because it gives you some, you can use it with neurofeedback. So if you detect how somebody is, for example, reacting on something, you can change the surrounding. Research and development, you get more insight of the brain activities. Of course, most of the reason why employees start at Snap is because they want to help people. This is, of course, our main focus, but I always don't like to say it. The reality is you have to earn money, and it's not that easy to earn money with, for example, a control unit for an exoskeleton, which sells 10 times in Germany. We would have to sell it for 100,000 euros, and nobody is paying that. So this is why we love this topic, but we somehow need to have a broader approach in this field in order to get the power on the road. Okay, so when we started with, I don't know if you have heard of Rexo and Waves. These were two, oh, only 10 minutes left. Okay, now I need to. So we started also synchronizing IMU data to our EEG, and we trained an AI for detecting certain movements. And as you can see here, the AI detected very good the movements. We built the IMU devices ourselves back then. So we first did AI to detect the movements, and we did everything to detect them, and it worked very easily, not very complicated stuff. And then we synchronized it with our EEG data in order to label the EEG data to certain movements. Here you can see it. I don't know if you guys can see it. And we detected it with a software which we built synchronously, and then we were able to very easily train our EEG data. So the movement detection was just for, like I said, labeling. We also used the IMU data to control stuff in a VR, which we did in the Rexo and Waves projects, which where we have, where Christian put up the VR scenario over there. So I don't know if you guys have tried it. And we used these labels also to control the VR. So that's the only VR video which I have in my PowerPoint here. Okay, so what we did is we built a software to measure the EEG and IMU data. We trained some neural networks, and then we did the inference. And like that, we were able to go farther in these steps. Here you see our experimental setup, what we did with that. So as you can see here, if somebody moves their hand, different regions in the brain get active. And we did play the Pong game. We built a Pong game to control. And here you see Ronja moving this cursor. I don't know because of the lightning if you can see it, but she moves this cursor down here by thinking of moving her right arm to the right and her left arm to the left. So this is motion imagery, and I show you this video because it was for us the most impressive one. We did it only with 8 electrodes, and it's real time, and the training session before took like 10 minutes. We also do this with real movement, which means we actively move our hands and get out the EEG signals, which is also interesting, but not so nice to show. But also some say this is not nice to show because you cannot see anything except, well, but she's thinking that, okay. What we also did is, like I said, we have the IMU sensors on our hand, and we were doing experiments moving the right hand and the left hand. And what you can see in the video behind me in the yellow line is the relative movement of the IMU sensors of the left hand. And what you see on the blue line, you see the calculated EEG direction. So we get the direction out of the brain, and it's pretty similar. It's not exactly similar, of course, not because it's really complicated to do that, but we're very happy that we got this so far. Okay, so we are able to get out the real movement out of the brain, and we get out the motor, the imagined movement out of the brain. And it's very, very difficult. It's like, well, for us, it was not so easy. I don't know how for the others, probably not, because otherwise that would already exist. But what we also do is we also use the artifacts to control the system. We, for 2 or 3 reasons, we use that. One reason is when we use the artifacts like the eye blink. For example, here you see Rehan controlling our helicopter, and he uses his eye blinks to control it, that it doesn't get too much down. Or we play other games because we know that it will eventually be some kind of hybrid system to control a BCI or a VR scenario, for example, or another computer game or something. Here comes my last video, where you see, and I know eye blink detection is nothing great or new, but for us, we use it also, we detect it with AI, which is maybe somehow some new, and we use it to control it. And here what you can see is also, it's not a direct eye tracking, but what I didn't say is that when you measure the EEG and you move your eye, you have a big dipole in the EEG, or the eye is a dipole, and you can see it very good. And we also trained the AI to get the eye direction out of the EEG data. Yeah, which is a nice thing to have a hybrid system. But in the end, I think the most important task what we face with BCI is to think out of the box. Because when for example, when I'm in a VR scenario and I want to go to Sebastian's office, I probably would never stand up, go to the door, open the door, go to the other office, open the door again. I would think I want to be in Sebastian's office. So I think it's very, very important to, when we try to find new commands to get out of the brain, that we also think, what are we going to control and how are we going to control it? Because, I mean, in the VR, and that's the nice thing, the sky is not the limit, right? We can do whatever we want. If I want to let myself wings grow, I could somehow build an AI, get it detected, and let myself in the VR wings grow. It's really a nice thing to think about it, that we would not use our physical boundaries anymore to get around in the VR. And yeah. Okay. Oh, I also have this, which is not a nice. We of course face a lot of challenges in the BCI. So as I said in the beginning, dry electrodes would be wonderful, and the signal from dry electrodes would be great. That's really, really, really important. Only few electrodes would be also great. If I could only get it from, I don't know, some electrodes here, but we don't. But that would be also very cool. The accuracy is not as nice. It's also very difficult. What we do is, right now we cannot train with the same AI and take 2 people. So we do train it for each person, which is also maybe the reason, or the reason for that is maybe also because we have so few EEG data. Once everybody here is equipped with an EEG headset, it will probably change, but so long we are not having that. Yes, and maybe also what we are not thinking about is we need to think more of edge computing and where to position the AI, because if everybody would wear EEG headsets and we would all transfer our EEG data to somewhere to the cloud, which we probably even don't want, especially in Germany, that would never do that, then we would have to think of bringing the AI in the headset, which is luckily, I think due to the chip development soon, very, very easy to do. Yes, and again, a little bit to our company. We were founded in 2010, so we have some time already. We are not a real startup anymore. We have a very, very nice, friendly, big team, which involves way more than the people which are here. And we don't only do BCI, we also do AI-based hardware and software systems for the industry, because we have to earn money. Yeah, that was it. Thank you.
Thank you so much. I'm sorry. Okay, so we're back. Thank you so much. It was so insightful. Are we back on track for questions? Wait a sec. Art, do we have? Okay, so everybody who is as inspired as myself from Corinna's talk, just find her in the next break. And we're going to